In this video, we're going to talk about static typing versus dynamic typing. One way to think about the purpose of static type systems is to prevent common programming errors. And they do this at compile time. So they do this when the program is compiled. And in particular, they do it without knowing any input to the program. So the only thing that is available is the program text. And that's why we call them static, because they don't involve any of the dynamic behavior, the actual execution behavior of the program. Now, any type system that is correct, any static type system that actually does the right thing, is going to have to disallow some correct programs. It can't reason completely precisely at compile time about everything that could happen when the program runs. Now, what this means is that some correct programs, and by that I mean some programs that would actually run correctly if you executed them, are going to have to be disallowed by the type checker. And so for this reason, some people argue for dynamic type checking instead. And this is type checking that's done solely when the program runs. So at runtime, we check whether the actual operations we're executing are appropriate for the actual data that arises when the program executes. Other people say, well, the problem is really just that the type systems aren't expressive enough and that we should work on fancier static type checking systems. And over time, there's been considerable development in both camps. We see a lot of new dynamically checked languages coming out. So a lot of the modern scripting-like languages and domain-specific languages have some form of dynamic type checking. Other people have been working on fancier and fancier type systems, and actually there's been a lot of progress in static checking. The disadvantage of the more expressive static type checking systems is they do tend to get more complicated, though. And not all of these features that people have developed have actually found their way yet into mainstream languages. Now, one important idea that this discussion suggests is that there are two different notions of type. There is the dynamic type. That is the type that the object or the value that we're talking about actually has at runtime. And then there is the static type, which is the compile time notion, what the type checker knows about the object. And there is some relationship that has to exist between the static type and the dynamic type if the static type checker is to be correct. And this relationship can be formalized by some kind of a theorem that proves something like the following. What we'd like to know is that for every expression E, for every program expression E that you can write in the programming language, the static type that the compiler says that that expression is going to have is equal to the dynamic type of that expression. Another way of saying that is that if you actually run the program, then you get something that is consistent with what you expected to get from the static type checker, that the static type checker is actually able to correctly predict what values will arise at runtime. And in fact, in the early days of programming languages, these were exactly the kinds of theorems we had for the very simple type systems in the languages at that time. Now, the situation is a little more complicated for a language like COOL. So let's take a look at the execution of a typical COOL program. So here's a couple of classes, class A and a class B that inherits from A. So B is going to be a subtype of A, which we'll write like that. And now we have a declaration here of X having type A, and this is the static type of X. So the static type of X is A. All right, and that's what the compiler knows about X's value. And then here, when we execute this line of code, we can see that we assign a new A object to X. And the fact that it's new is not important. All that's important is the fact that it's an A object. And so at this point, the dynamic type of X is also A. Okay, so at this line of code, when it actually executes, A, which was declared to have static type A, actually holds an object of class A. But a little bit later on, down at this line of code, the dynamic type is actually different. The dynamic type here of X is going to be B. Okay, when this line of code executes, X holds a B object, even though it's declared to have a different type. And this is a very, very important distinction to keep in mind. So there's a static type, there's a type that the compiler knows about, and that's invariant. X has type A, it always has type A. All the uses of X for the entire scope of X are typed with class A by the compiler. But at runtime, because we have assignments and we can assign different objects to X, X can actually take on objects of different types and different runtime types. So here's an object of type A, and here's an object of class or type B that's assigned to X when the program executes. What this means is that the soundness theorem for the cool type system is a bit more complicated than the one for simple type systems. So in the presence of subtyping, the property that we want is that the static type computed by the compiler for a given expression E is going to be a correct predictor of all the possible dynamic types that E could have. And we do that by using the subtyping relationship right here. So we say that whatever dynamic type E could have, whatever types E can take on at runtime, they have to be a subtype of the single static type that is predicted for E. What this means is that all the operations that can be used on an object of type C have to also be able to be used on any object of type C prime that's a subtype of C. So if C defines certain attributes and methods, then all of those attributes and methods have to be available in C prime. Okay? And therefore, subclasses can only add attributes or methods. So whatever attributes and methods a subclass will have, what C prime in this case, those are all in addition to whatever C has. So C prime, a subclass, will never remove an attribute or remove a method. It will only extend or add methods and attributes to the class it is inheriting from. And note that you're allowed to redefine methods in COOL and in most object-oriented languages, but you cannot change the type. So even though you can redefine the code that goes with that method, it still has to type check according to the original type that you declared. And so whatever type the method has in the first class in which it's defined, it's going to have that same type, that same argument and result, the same types for the method arguments and the same type for the method result in all of the subclasses. And that's a pretty standard design point for a lot of object-oriented languages.